And today we're going to talk about convergence. Apologies for my handwriting. It's a new iPad. I haven't figured out how to use it yet. I'll get there. Okay, good. Good morning, class. No? Good morning, class.
Good morning.
That's better. We last time we talked about MCMC and like how it works and what kind of problems it solves, and every question was actually about convergence. So I realized we should probably just have a session about how do you know that your MCMC is good. Many people in this room actually use MCMC more than I do. So I have opinion, as you'll see, I have strong opinions about this matter. Also, I've written a note about it. Well, I've written a note about MCMC in general, which is with Foreman-Mackey. So there's a paper by Foreman-Mackey and me. And it's called like Data Analysis Tutorials Using MCMC. So it's got using MCMC. Because it's supposed to be like a user's manual for MCMC that I believe that this is the only paper in the refereed astronomical literature that has exercises. I don't know, I might be wrong. By the way, on another topic, I believe that I have the only paper in the astronomical literature that contains a picture of a kitten.
It's
It's in the refereed literature, but it is an April Fool's paper. But anyway, this apparently I'm not supposed to. Andy Casey was saying these tutorials are not supposed to be just me talking about my papers. So okay, fine. So we're supposed to talk about MCMC, and let me just remind you, because it's going to be relevant to what we do next, that when you have a good MCMC method, when you have a good sampling, remember that. So I said. And not everyone is here. I just want to set the stage. What does it mean to have a good sampling? Because this is very relevant to our question. A good sampling means that there are integrals that you want to do that look like f of theta, p of theta, d theta. And you can approximate these very accurately with a sum that looks like this. If this integral, this is some all positive function that integrates to unity. This is a probability distribution. But you can think of it as an integration kernel or a metric for your a measure for your integration. So this is an integration measure or a probability distribution, and you're integrating this function that you care about. This is something you care about. It's like, maybe you're just getting the mean of your period distribution or the mass distribution or something like of the mass, posterior mass or whatever. This is something you want to know about this probability distribution or about the parameters of your model. If you can well approximate this integral with this sum, then these values, theta I, are a good sampling. There are actually other conditions that the sampling also needs to make, but this is the one we really care about in most scientific applications. Then theta I are drawn from P of theta. So these theta come from P of theta accurately enough. If this is accurate enough for you, then this is accurate enough, you're good. That's my point of view on what a sampling is. I have some other comment to make about that. Well, one comment to make about it is that notice that what constitutes a good sampling depends on how bad this function is. That's one comment to make. So it's subjective. It's a subjective question whether your sampling is good enough because you have certain things that you want to compute. Second thing to say is people often don't think of samplings like this. People think of the samplings as just showing them the posterior distribution. You just plot the samples. But when you're just plotting the samples, you are implicitly doing integrals like this. Because say you plot a histogram of your samples. What is a histogram of samples? It's the number of samples in the bin. You want that to be equal to the integral of the probability distribution over that bin. So when you're plotting a histogram of samples, your f of theta is a set of top hat bins, and you're doing the integral of the probability distribution in those bins, and you're doing it by counting the samples in the bins. You see, so the things you do with posterior samplings are integrals, and you want them to be good. Good? Everyone on the same page? Great. And then we talked about MCMC, how it works, methods, things like that. So what happens when you do MCMC? So when most MCMC methods, by the way, there's Markov chain. There's Markov chains. Don't care about that very much. I mean, it's relevant to MCMC. The Markov chain part, it's going to matter in just a second why it's a Markov chain relevant. Monte Carlo is a way of doing integrals. This is like a Monte Carlo of this. This integral approximation is a Monte Carlo approximation because you have random samples and you've taken random samples from your probability distribution and they approximate your integral. So that's the sense in which it's Monte Carlo. The sense in which it's Markov chain is that it produces samples in a sequence, and those samples are going to have some autocorrelation. They are not independent samples. They will depend on the previous samples. So that means if you have a MCMC method, it means you actually produced a sequence of samples, theta 1, theta 2, to theta n. And there is some autocorrelation, meaning these samples are not independent. At least the way to think about it is there's a sequence of samples and nearby samples are going to be more correlated than faraway samples. Actually, they have to be. It's not just that they're going to be, they have to be. The correlation between these two samples has to be less than less than or equal to the correlation of nearby samples. Like because of the way Markov chain is set up. Because a Markov chain only has local state and you're updating a local state. And anyway, it has to do with that. You can't. And so even though you've produced n samples, because they're correlated, you don't actually have n independent measures. We talked about that last time. So really, there's kind of an effective number of samples, which is kind of the number of samples you have divided by some autocorrelation length, which I'll sometimes call the autocorrelation time, but it's not really in time units. It's the autocorrelation time is the number of samples you have to go before you kind of have an independent sample. And there's explicit definitions for this object, which should be right now. Yeah, go ahead.
Is this in general true that if your samples are correlated, that your error is always larger? Aren't there methods where you want like correlated samples in a certain way, but still they give you quite good?
Actually, that's a great question. Ryan and I are working on a very related question on stellar noise. I'm not sure. So one thing I'm pretty sure is true is that if you could set up your sampling so that there were negative correlations between nearby samples, then you can actually beat n. You can do better than n if they're negatively correlated. It's almost impossible to set that up with the MCMC methods we actually use. There might be some other edge cases where somehow the correlations don't hurt you. Like I think there might be some situations where the correlations don't hurt you, but I haven't figured out what those are. That's out of scope for me. Generally, when you're thinking about like square root n on this interval, to actually figure out the error analysis on that interval, like how well did I do that interval without sampling? It's actually quite hard to figure that out, but it's unlikely to be better in a fractional sense than the square root of n over tau. Like the square root of n effective is really the thing that's going to set the uncertainty on the integral, unless you're very lucky. Like that function f might have some weird properties, unless it does. Yeah, anyway, the true, by the way, the estimation of like how well you've measured that integral is itself a whole area of research in Monte Carlo integration. Some integrals are very hard to do with Monte Carlo. By the way, one thing I said last time, and it's going to be abundantly true now, is that MCMC is a method of last resort. If you can do your integral any other way, you should. And in the applied math community, nobody uses Monte Carlo methods unless the integrals are very large in dimension is the only places that Monte Carlo methods are used. And Markov chain Monte Carlo is somehow even worse in some ways. We have to use it in our problems because it's adaptive. Like the Markov chain aspect of it makes it adaptive to our problem. But if you can do that integral by just like quadrature or brute force, you should. It's way better. Okay, good. So let me draw a picture and then we will start to have something to talk about. So imagine I have some parameter space here, and here's my parameter space theta, and I've done my MCMC sampling, and I'm just going to draw a two-dimensional space because I have a two-dimensional board, and I get some, and then I plot my MCMC, I run my MCMC, I'm pretty happy with it. I'm going to plot my MCMC here as a histogram, and I'm going to contour that histogram, and I see something like this. Not an uncommon situation. Something like this. So there's like lots of samples here, lots of samples here, samples in this banana shape, no samples out here, no samples down here. So I've pretty well constrained my quantity. It's pretty good. It's a little bimodal, but not terrible. This is a pretty typical situation we get in like exoplanets. For some relatively low signal to noise thing. And you could draw like the projection of this histogram down to one axis and you get something like, sorry, my hand is so shaky today. You get something like, like this. Something like that. That would be like the projection of this down onto this axis, which I've done in the wrong way if you're used to using corner. Should have put it on top. Anyway, so this is like theta 1. This is the first element of theta. There's my distribution. How do I know whether my MCMC sampling that made this plot is good?
Plot trace plots.
Say again?
Plot traces.
Traces. So traces meaning over time, right? Like the sequence of so you can do that. Whoa. So we could have plotted, so we took the samples are taken in order, as we said, and there's correlations among them. So the time ordering of the samples matters. So this is like I, which sample you are. And now you can plot theta I. Now, let's plot this axis. So this axis would be theta 2. This axis is theta 2. So now I can ask, for each sample, there's a sample here, sample here, sample here, sample here, sample here, sample here, sample here. So I can see the samples moving with time, and it will look something like this. It'll look something like this, right? There's a lot of samples down here, which formed this hump. And there's a lot of samples up here, which formed this hump, right? It'll look like that. Are we converged? I would say no. What's your argument?
Well, it's oscillating.
Well, it's always oscillating, right? It'll always be oscillating, right? Because this is one Walker. Oh, by the way, if you use MC, of course if you use MC, the sampler that we love here, you have a set of walkers. So you can think of this as one walker in MC, or if you're doing traditional Metropolis Hastings, this is just your sampler. If it's sampling this correctly, it will be going back and forth between these modes and exploring these edges. So it will be oscillating. The issue is not that it's oscillating. The issue is that it only oscillated a few times. And so all of these samples here are in the one mode. All of these samples are in the other mode. That kind of suggests that you have an autocorrelation time of something like this. You see, you can just see it in a plot like this. That suggests that your autocorrelation time is something like this. Tau is on that order, just roughly, just looking at it. And that suggests that the effective number of samples you have here is maybe, I don't know, 3, 5. We can say a lot of technical things going forward, but if it looks like this, you're not converged. That is like almost the most important thing about MCMC. Now, what are your options here? Yeah, go ahead.
So if one mode was much more
Yeah.
significant than the other,
Yeah.
it would spend more time in that mode than
For
the
sure.
other, and then you would kind of infer two different correlation times for the two different modes.
Right. I've given myself an easy case here. Most cases are not this easy. Most cases, it's like there's a mode and there's some big tail or something. And then you're asking, like, how often does it go out into that tail? Basically, if it rarely goes out into that tail, your autocorrelation time is long. If it goes out into that tail frequently, it's shorter. Now, of course, if the tail gets really low probability, it won't go out there very often just because it's low probability. That's why this kind of heuristic is not quantitative. Because if I had made this mode 10 times bigger than that mode, then the fact that it spent a long time in this mode wouldn't be so informative. There's even, but tests like this are good even for unimodal. Like even if you just have like a Gaussian looking thing, if it takes ages for the sampler to get from one side of it to the other side and back, then your autocorrelation time is long.
Are you looking at what one walker is doing here?
Yes, this is one walker. You actually, one of the problems with this that's very important is if you do this, you have to preserve your time structure. So like sometimes when we use MC, we have many walkers and then we like combine them in some way that destroys the time structure. But you really want to think of each walker as having its own time structure. And actually what we usually do is if you have 40 walkers, we'll plot here the lines, not dots, but lines, colored lines for several of the walkers. And then you see that the walkers are changing modes and stuff, but if they're doing it rarely, you don't have many points.
But would including more walkers maybe make this duration of sampling sufficient?
It might, yes,
Yeah.
because even though I'm only getting 5 here, if I was running 10,000 walkers and all 10,000 were doing that, then I would have of order 50,000 samples instead of 5. Yes, that actually the nice thing about, again, provided it's burned in, there's also a burn-in issue, provided that, and we're going to talk about burn-in in a second, provided that it's burned in, then yeah, every walker you get to treat as a separate set of samples. And the walkers aren't correlated actually in this sense. They have weird structure, but they aren't correlated in this sense. By the way, if you use MC, I want to just say, because it's MC is my, oh, nice, now, I guess I still need to learn things about this iPad. I think the class is over. Oh, no, it's not. This is like a real aside, because this is really only for MC users. You know how MC is a highly used sampler in astronomy, and it's an ensemble sampler, which means it's using the collection of samplers of different walkers to decide what to do with each walker. So each walker makes a decision based on the other walkers or some subset of the other walkers. And when MC is not converged, the distribution will look like this. It's very common. I see this all the time. it will look like your distribution. It'll be like a ratty version of your distribution, but then there'll be a set of walkers there and a set of walkers there and a set of walkers here and a set of walkers here. Like it'll have like paths of walkers like this. Also, if you are not burned in, you will sometimes see something that looks like this. And you have your distribution, but then there's like this funnel, and it turns out that you initialized here. So like if you initialize your walker here and you can still see the path that it took into the thing, then you're probably not converged. Or there's a burn-in period at the beginning of your samples that you need to take out. So again, when you plot, so the Sabina's suggestion that you should start by plotting this is a very good idea, because sometimes you'll find that you actually, it looks like this. Because you started in some crazy place and it went down and then got into this mode. And if you see that, usually you want to integrate longer and cut off the beginning. And you don't usually want to cut off the beginning here. You should cut it off like here, because you're probably still contaminated by that here. Actually, you can be contaminated by it for a long time. You might think, oh, I've come into the distribution here, I'm good. But remember, you're only plotting one variable here out of a large number of variables, and there's the curse of dimensionality. So there's things going on in the other dimensions. And if you're not burned in, if you're just barely burned in this dimension, you're probably not burned in the other dimensions. And so probably there's other things going on. So usually you want to be very conservative when you see things like this. Of course, yeah, there's some real world things I want to say about it. But anyway, good. Questions, comments? Yeah.
You're talking about convergence between the wells that you found, but you haven't talked about coverage guarantees.
Right, good, yes, good. Which is, I think, also related to burn-in somehow, but let's talk about it. So good. So here's something that happens. So here's my space again. Here's my theta space. And now I'm going to do two samplings. I'm going to run two completely different samplings. Maybe there's two. Actually, Tiger, is Tiger in there? Yeah. Tiger was showing me a problem where they did two samplings with two different methods and they look totally different. And the question is like, what's going on? And so like one person does a sampling and they get, this. And another person does the sampling and they get this. That's a sign, that's a strong sign that these are not converged and actually it's also a strong sign that there might be a lot of bad structure in your space. Like this is a very unfortunate situation when you get this, because you're quickly going to get to a situation where you provably cannot sample your problem. So for instance, let's imagine that both of these samplings are actually good. You might think, well, they can't both be good, but they can in a certain sense. If there really is an isolated probability region here, this could actually be a good sampling of that. Like if you look at the time history of this, it might do all the stuff you want it to do. It has a beautiful autocorrelation time. It's good. You have lots of independent samples. And this one might also obey those rules, right? It might be that the sampler went back and forth in here. It's all good. It's well sampled. It's great. It just is that there's a valley between these that's so hard to cross that the sampler never crossed it. If that's the case, life is bad for a number of reasons. One reason it's bad is effectively you have two models here. You don't have one model, you have two models. And you would have to combine these models somehow using some evidence integrals that are quite hard to compute. Another reason it's bad is if you believe there might be other islands here, how do you find all the islands or the best island? That gets into discrete optimization, and discrete optimization, there are theorems, which are these no free lunch theorems that say there is no way you can find all the islands. except by brute force searching every single part of the parameter space. And you might think, oh, no problem, it's two-dimensional. But if your problem is two-dimensional, you shouldn't be using MCMC at all. You should just be integrating. So really, this is just a projection of some much bigger problem. And probably there's islands in your space. And the only way you can be sure that you hit all the islands is actually to search the whole space.
So wouldn't it be nice to have a guarantee that you didn't miss an island that's bigger than some minimum size? Based on
That would be lovely. It would be lovely to have that. Actually, no, let me say, there are some cases where you know how big the islands are. So in general, you don't know how big the islands are. So in principle, there could be, I think I need to reset some of the settings on my brand new iPad. In principle, there can be an island, I want more colors. In principle, there could be an island that is incredibly tall and incredibly narrow right here. So actually all the probability is right here. You just never got near it.
You can often soften your problems to prevent that.
Good, I want to talk about an exact case. Right, you could in principle do something to soften, like there are these ideas of annealing. Actually, annealing, somebody mentioned, maybe it was Sabina, somebody was saying that they always use a parallel tempered sampling. Wasn't that you? Parallel tempered sampling is a method that makes these things softer, and then they are more likely to get caught, and then makes them harder again. But even those make a set of assumptions, so you can adversarially miss. There's always things you can adversarially miss. That's the point of the no free lunch theorems. There's no way you can write down a problem. However, there are some problems with very good structure. So for instance, Adrian and I have a problem called the Yoker, where we're looking for frequencies in radial velocity data. We're looking for orbital companions in radial velocity data. And there, the width of the modes in one dimension, in the frequency dimension, is actually set by signal processing. It's set by the uncertainty principle. Like if your data set is longer, the modes get narrower. So we can actually compute how narrow the modes are. And we actually brute force sample at the density such that no mode can get missed. So like that's a case where we have true guarantees. We know what the width of the mode is from like the uncertainty principle of the Fourier transform. And then we can guarantee that we get all modes. So there are some places where you can get guarantees, but it's very rare. That's a rare situation. But yeah, go ahead.
Yeah, you don't have to spend time on this, but one thing that I noticed going into the search for pretty frequently is that they really love AGVI, variational inference.
Yes, variational inference, yes.
Which is not as widely used in astronomy.
That's true. Actually, that's a good point, that we should do a variational inference class.
Yeah.
Because variational inference has a completely different set of problems than MCMC. But it's very interesting. So I just wanted to finish responding to Sadri that in general, when you have these problems where if you start the sampler at different places, you get different posteriors, you either have a very hard problem that will be very hard to solve, or you need to go to a method that somehow does something that softens things and hardens them back up again. The examples are parallel tempered, annealed, whatever type things, and nested sampling are methods that try to find these modes
And
find
noise.
them. Say again?
And adding noise.
Yes, and sometimes you can just, there's very related to tempering. How does tempering work? The way tempering works is it effectively takes the likelihood function to a power that is less than 1. So if you do the 8th root of your likelihood function, it's like you had 1/8 as much data. So that's what tempering methods kind of look like. Because you work in the log of the likelihood, so it's actually just multiplying the log by a factor, which is less than 1. And that's how it softens the modes. But you can also soften the modes by dropping data. So one of the funny things in the Yoker is that we can sample with a subset of the data, and then we know that our final posterior has to live inside the posterior of the worst data set.
Yep.
So you can noisify your data, inflate your error bars, or drop data points, and generally these things will get dropped. But in order to say that, actually, there's going to be a set of like, oh, I can't operate this into this. apparently you're not supposed to make the first time you ever use your brand new piece of technology while you're in front of the room. But anyway, if you have situations like this, yes, let me just write it because it's all the things I just said. You want to be doing something like tempering to deal with this, but even that's not guaranteed to give you an answer. Stop it. I'm not about to write on this page. Wah. Oh, good. Our AB is dead. It's my fault, though. Somehow it's my fault. Oh. Interesting. Sorry, you're going to watch me try to keep up. My pencil is connected.
Is your pencil charged?
I have no idea.
I've had that happen with Notability as well.
It might be a Notability bug, yeah. Got it. Tempering, there's this thing called nested. And then there's things where you like you sample and combine. Meaning I try to separately sample the different modes and then combine the modes. And then there's a fourth thing you can do, which Sadri just suggested, which is you somehow like soften your likelihood. Oh, there's another thing you can do, which is what we do in the Yoker, but it's a really, really bad idea. So I shouldn't even say it out loud, which is you can import and sample. The way the Yoker works is we actually do a prior sampling of the entire prior space, and then we downweight them with the likelihood function. That's an extremely bad idea. Don't ever do that. We do it in the Yoker because we needed we needed some provable properties of our sampling. But if you don't need provable, by the way, important sampling is interesting if you want guarantees. This thing, important sampling, can sometimes give you guarantees. So in the Yoker, we have guarantees that our samplings are correct. They have autocorrelation time of 1 correct samplings. We have guarantees in the Yoker, but it comes at enormous cost. Like we caused the Western world to pass through 1.5 Celsius. Only do it if it really matters. Actually, one of the problems is, yeah, anyway. Okay, good, great. Good. By the way, these problems are the same problem, Sadri. This problem here of like your autocorrelation time is long is the same as this problem that you don't have coverage, because this is just that your autocorrelation time is extremely long.
Yeah, I just mean that most metrics of deciding if you're converged will never detect this, but they
Good.
could detect the other one. And I think that's an important
Yes,
distinction.
good. Great, absolutely. That's exactly, yes, very good point. That Sadri is making a great point here, which is that a situation like this blue sampling can pass all of your tests, even though it's definitely wrong because it didn't include the green and red regions. It can still pass all of your tests because the autocorrelation time estimators, and I can write one down, we maybe should write one down, but the autocorrelation time estimators can't see autocorrelations that are on a longer time scale than your sample. So like if there really is on a very long time scale, this thing would jump into a different mode, you'll never see that in a sampling of this length. And it's very related to, in cosmology, you can't observe modes in the large scale structure that are bigger than your survey. And there can be modes here that are bigger than your sampling, no matter how big your sampling is.
Can't you just solve that problem with adding more walkers?
It depends how much they're separated, right? So in principle, if you have, in principle, the Metropolis Hastings algorithm we wrote down last time has a guarantee. It guarantees that it will sample the entire posterior in the limit of infinite time. But that doesn't give you any quantitative way of saying how far away is infinity. So if you do 50,000 samples and you're not good, so you go to 500,000 samples, that won't, and everything looks the same, that's great, but it doesn't mean you're correct.
If you know something about how big your islands could
Yeah.
be, then couldn't you start with a grid of the walkers
Absolutely.
or something?
That's right. So in some cases, you know how big your islands can be. It's rare, those cases. But as I was saying, in the Yoker, we actually know it comes from the uncertainty principle. We have whatever, 9 years of SDSS data. So in frequency space, the modes have a size of 1/9 years. It's just like astroseismology. And therefore, what we do, that's why we do this important sampling where we actually start with a prior sampling that's so fine that we're guaranteed to hit every possible mode at that resolution. And then we know we aren't missing any nodes. We kind of can prove that we haven't missed any modes. That's rare though. Actually, by the way, there are a lot of times when you know a lot about your posterior, like sometimes you know your posterior is Gaussian. Then you should not be using MCMC. If you know your posterior is Gaussian, you're done. Just measure the mean and curvature of that Gaussian and you know everything about it. MC you're using, in my assumption here is that you're using MC because there are things about your problem you don't know. And once there are things about your problem you don't know, usually you lose those guarantees. Although Sagery is right that you do have a guarantee that if your data are less informative, the modes get bigger. And that's the idea that underlies parallel tempering and nested sampling, is that like the one guarantee you do have is that if you have less data, you will have an easier job of sampling it. Oh, by the way, that's an amusing thing about sampling. It's better at low signal to noise. This is a very important fact. It's better for many reasons. One is at low signal to noise, your posterior will be less Gaussian, so you need to sample, but also at low signal to noise, your posterior will be bigger. And so it's easier to sample. When you get to really high signal to noise, your posterior becomes very close to a Gaussian and very hard to find. So at high signal to noise, you should be a frequentist and just find the correct answer. At low signal to noise, you should be a Bayesian and sample with MCMC. This is a realization that I think we are going to be having after Gaia DR4. Because after Gaia DR4, there's going to be a ton of high signal noise objects that people are going to be sampling the crap out of them and failing. So after Gaia DR4, you should either work on the low signal to noise objects, which is very exciting and no one else is thinking about, except maybe So in here is thinking about them. Or you should become a frequentist and run with astronomers. Yeah.
In cosmology, how often do you resort to anything other than nested sampling? I'm seriously, like, practical advice, how?
You know, the funny thing is I have never used nested sampling and I do not believe. So I actually don't ever use that tool.
Can you elaborate?
No, not really. I mean, in the sense that the nested sampling is very Baroque. The method is extremely Baroque and it involves all this like splitting the prior space into things above and below thresholds in the likelihood function and stuff, which is like, it does a lot of complicated things. I feel like parallel tempering type, it's very similar in its action to parallel tempering, and parallel tempering has a very simple description in terms of statistical mechanics. Remember, these MCMC methods come from statistical mechanics, right? They're like you make a bolt. It's like what Maxwell and Boltzmann were thinking about for like molecules in a gas. You're making the walkers run around as if they're molecules in a gas. And parallel tempering retains that physical interpretation. So that's why I tend to go towards that rather than nested. But I don't really have opinions about methods. I more have opinions about whether or not you're okay. You know what I mean?
Do you have any references to read up on?
I can make such reference. The goal is, I'm being very bad about this, but the goal is that the document will contain the notes and references and the video. And it currently doesn't. Except
It's a
the
large
time,
cow.
except the time that Andy Casey did it, because Andy Casey is a responsible member of society. Actually, one thing we've learned since hiring Andy Casey is that he may be the most responsible member of society. But anyway, so I will put references up for all of these. Yes, I do have references for all of these. Actually, the one I don't have a very good reference for is the sample and combine. I've been actually meaning to write a paper about that.
Sorry, do you mean by that when you end up with these, find the individual modes with individuals, then how do you put them together? Is that what you mean by that?
Yeah, exactly. So the method that I've been working at a very, very slow, I don't want to share the password. On a method that takes this, discovers that there are multiple modes, tessellates the space, treats them as separate models, samples them trivially with an easy sampler, and then combines them at the end of the day. That's something I've been working on. That doesn't exist yet. But there are things in the literature that have done related things. But certainly for tempering, nested, and softening the LF and importance sampling, I have examples for all of those. And then the other thing we talked about last time is Hamiltonian Monte Carlo, which is something you need to go to if your parameter space gets very large. Like if the parameter space gets large, none of these methods actually work.
But by large, you mean 15 or more?
I mean, yes. I always say 12. If you're above 12, it's large. Of course, a lot of people in the room are above 12, and so now they're feeling nervous. So maybe you can get to 20, but if you're in the many dozens to hundreds, you're definitely large. And then these methods just don't work in practice, in my experience. None of them work. Like for instance, there's a great example problem that's done a lot in exoplanets, which is when people have like 7 planets. You know, actually, John laughed because he has 9 planets. But anyway, when you have more than something like 5 planets, you're starting to get to be a lot of parameters. And then people try to sample it, and the samplings that are done with different methods are not consistent in those problems. And so since they're not consistent in those problems, I think they're actually impossible to sample. And there you're talking about like 25 parameters. Like 5 planets, typically you have 25 to 30 parameters. And so, yeah.
Maybe this is a bit naive, but I mean, in gravitational waves, we use this also, and you should have done this in the first place, but your likelihood has degeneracies, right? Mm-hmm. And like, for example, sky position, we understand very well in which parameters these degeneracies lie. So you can fold this, right, and then unfold it in the end. Very, very good. Good. Often, when you have a situation like what I've shown here, there's actually a surface here that goes like through these 2 solutions, such that this isn't always true. This isn't always true, but when you see a situation like this, or even if you go back up to this situation where there's like a banana, it's always a good idea to think, is there anything special about this curve? Like sometimes in exoplanets, like this curve is the aphelion distance is constant, because really the data are measuring the aphelion distance. They're not actually measuring the period or the eccentricity or whatever. Like there's a lot of problems where like there's a feature you haven't thought about that's in your model that actually makes these 2 models actually very similar. And then often you can reparameterize and get rid of them. So in this case, like this might be a very bad sky position plot, and actually this is clustered in the southern hemisphere and this is clustered in the northern hemisphere, and actually it's the same direction to the object, but because it was like normal to the LIGO experiment, you didn't see the time delay or whatever, and so you can't tell whether it's that way or that way.
So it's always worth looking to see if there's a reparameterization, because sometimes bimodalities disappear. Another terrible bimodality that we hit all the time in astronomy is, everyone's gonna laugh, but it turns out this is actually very hard to deal with. You have an angle theta, and your posterior looks like this. And every time you have this, your friends will laugh at you. They're like, you're an idiot. But actually, if you have a lot of angles in your problem, or if you are doing a lot of different systems, it's actually very hard to automatically identify and fix this problem. And we have opinions here about how we fix this problem. In fact, we usually take the sine and the cosine of this angle and pre-multiply them by another parameter. So instead of doing sine of this angle, we do the square root of the eccentricity times the sine of this angle, comma, the square root of the eccentricity times the cos of this angle. And then this thing becomes a vector in a two-dimensional space. And then this all collapses and you have a unimodal posterior. So sometimes when you have bimodal things like this, there's just a transformation you can do that ensures that you'll be unimodal. But in this problem is very hard to solve in general. Another problem that is like this, that's very hard to solve, and I don't know if it appears in gravitational waves, but this appears in exoplanets like crazy. Here's the mass of one of your exoplanets, and here's the mass of the other one of your exoplanets. And you have a posterior mode here. If you have that posterior mode, then there has to also be a posterior mode there, because you can swap the two planets. The names of the planets are not parameters. So they swap. And if you can sample this, but your sampling never hits this, then technically you're not converged. And a lot of people see this and they go, oh, that's dumb. We could just order the planets by mass. And then only the one that has M1 larger than M2 is the correct mode. So we just split the space like this and then only sample here. And you're like, cool, we've solved our problem. Like, no, you haven't, because you'll have a pair of planets that are similar in mass, and then you've put them right on a degeneracy surface. And you put right on the edge of your boundary, you've just put your sampling right against the boundary of your prior, and then your problem actually gets worse. Yeah.
I mean, in both of these cases, it seems like you could let your walkers cross that boundary and then redefine which one you call M1 and M2, or the 2 pi. You could let pi, theta sample beyond and then take the mod.
Very good, very good. Actually, this is a very good point. The MC sampler, which we use a lot, treats the parameters as if they are vectors or the elements of a vector. Angles are not elements of vectors. So this violates the vector space assumption of MC. That's why it does badly. But you could build a sampler that knows about the ring, and it would just have a different symmetry, and it would know about the ring. I actually have a student who's looking at that question right now. Like, if we know that this lies on a ring, or if two angles lie on the sky, like the sky position, make a sampler that knows about that geometry and just samples that correctly. So we're working on that a little bit. That's one of the projects we're working on. This one is calling out for something which I believe doesn't exist in the literature, but if people know, it's very interesting, which would be a permutation invariant sampler. A sampler that for every model point here, it realizes that it also has a model point there. That hasn't been done to my knowledge.
I feel like Will and I have that.
Do you? Because there might be something you could abstract out of that and publish in the applied math literature. Because we did a deep dive on permutation invariance, and it doesn't look like there's very good writing about it.
Yeah, our problem with that, again, is the degeneracy with the northern and southern hemisphere of the star. So the inclination and obliquity would have like different values, but like the same.
Good. Great. Good. So a more general thing that you're bringing up is that there's group operators involved. When you have an angle like this, there's a group, which is the rotation group, and that moves your parameters around. And as you say, when you do something crazy like go through a mirror reflection or something, some of your parameters change and some don't, because there's like an action of the group operator inside the space. And anyway, that's a great area of research. If anyone's interested in that, like bringing group theory into samplers, super interested. Almost all of our problems are extremely geometric. GR is covered in groups. Exoplanets are covered in groups. We have an exact 4-dimensional group symmetry in exoplanet work for Gaia that we don't know how to deal with right now.
Can you just take every sample and apply the group operator?
That might almost be correct. We don't know. We don't know whether that would be sufficient. We haven't actually done the math, but it might be. It might be that you can just randomly apply group operators, so that you take a sample and jump by a group operator or something might actually be sufficient, but there might be more clever things. There's a lot known about group theory. The other thing is there's invariance. There's things about your problem that are invariant to the group. And so you might want to separate the problem into the invariant part and the covariant part. Okay. Good. What did I want to say? I wanted to say something. The gold standard for deciding that your MCMC method is correct, but as Sagery says, it will not solve this coverage problem. The gold standard is to estimate the autocorrelation time tau. This is the gold standard in the sense that if you have a sampler where you can sample and you can estimate the correlation time tau, and tau is much, much less than the number of samples you've taken. If you can estimate the autocorrelation time and the estimate you get for the correlation time is much less than the number of samples you've taken, then I would say you have done due diligence on your sampling. I guess you should also do some restarts to just check that you always fall into the same mode. So let me just also add and restarts. Now, why? So we're going to estimate the autocorrelation time. I mean, I might not get that specific about it. I'll give you a sense of what it looks like in a second. Why do you want tau much less than n? And I mean much less. It turns out if you get an autocorrelate, if I just give you a highly covariant set of samples and you ask what's the autocorrelation time, you'll almost always measure an autocorrelation time that's like a third or a fifth of the length of the data I give you. If I have long correlations, I can just give you more and more data. And as they get longer, you're going to estimate a longer and longer autocorrelation time. You're always going to measure it to be about a third of the data I gave you. So when you get that your autocorrelation is a third or a fifth, so you said, can I just add walkers? So say I'm getting an autocorrelation time so that I only have like 3 effective samples. Can I take 1,000 walkers and then I have 3,000 samples? I'm good. Probably not, because if you're finding that it's a third of your data, probably you haven't estimated your autocorrelation time correctly. So you need to see that your autocorrelation time is substantially less than n, and I mean like a factor of 20.
You want that to be true without thinning. You want
right,
how much
without thinning. Now, then you can thin it. By the way, he's talking about thinning. If your autocorrelation time is 1,000, you don't have to give people all your samples. You can give them every 1,000th sample, and you're actually giving them just as much information as if you gave them all your samples. Of course, you feel terrible because you worked for weeks and you end up giving them 14 samples. And so sometimes you give them all the samples anyway, just so you can remind them that you did a lot of hard work, but there are only some number of independent samples. So right, you do the full chain to n without thinning, you try to estimate the autocorrelation time. If you get an autocorrelation time that's way less than n, then you can then thin at the autocorrelation time and give away those samples. And I believe you've done due diligence. As we indicated above, you're not guaranteed to be correct. But the important thing is you will never be guaranteed to be correct. If a referee says, this is not guaranteed to be correct, you can say, great, if we require guarantees, it invalidates a large fraction of the astronomical literature. And so no one can request that you have a rock solid argument that your MCMC method is correct. All you can do is due diligence. And I believe that due diligence is, well, this is even above and beyond due diligence. But this is very safe, very clean, is to estimate tau, make sure it's much less than n, and do that for multiple restarts and check that you have consistent posteriors. I actually think that is overkill in the sense that if you make plots like this, and the walkers really have explored the space back and forth thousands of times by the end of your sampling, these plots alone are actually very convincing. In some ways, for me, they're more convincing than any estimator you used for the autocorrelation time. So I actually think these plots can be fully convincing. But when we plot many of the problems that I've done in my life, when we plot the walkers, we get something that looks like this. So we're plotting a few walkers. One walker does this. And then another walker does this. This is very common behavior we see when we use MC. And when you have situations like this, you're definitely not converged. So, but if you see situations where the green and red walkers are like on the opposite sides of each other all the time and constantly changing which side they are with respect to each other, it's very convincing that you're doing well. And so then you really have you've met these two criteria without explicitly estimating. So it's not exactly that. So I'm lightening the load even further. I'm saying you don't even quite have to estimate it. It has to be obvious that your autocorrelation time is much less than n. As long as that's obvious, you're done. I don't actually think you need to explicitly compute it. We do when we're doing error estimates on the integrals that we're doing, but most people are not doing error estimates on the integrals that they're doing with their sampling. Julianne?
I mean, there has to be math that tells you you're in that mode, right? Because
Yeah.
it's something where like on small scales, your autocorrelation time is short, right? Or you know, it's not that many, right? Like if I take a small subset, I'm probably in the regime where it's just, you know, fiddling along.
Yes,
and
if
then
you
when I
took this, you would say, oh, our autocorrelation's short.
yeah, right. Like there has to be.
Oh, it's short, it's all good. But when you look at the whole thing, you're obviously not.
Do people traditionally plot their walkers?
It varies. It varies a lot, actually. I think people should plot their walkers. And now, if you have 200 walkers, this plot isn't very easy to read. So we usually just choose like
10 of them
6 random walkers and plot them. And often it looks like this. But then we need to go longer. But I guess I need to say, since we're at the hour, I need to say one last thing. Sometimes you make this plot and it looks like this, and you've used all the computation you're going to use this year. Like for instance, maybe this took 4 months to execute, right? That happens. Or maybe the SCC is cutting you off. Or maybe the United States has collapsed into civil war. But for various reasons, you might be done. You might never be able to do it again. And this is what you have. What do you do? And by the way, there's a whole bunch of papers in that category. There are papers in cosmology, like in dust maps, 3D dust mapping. I'm looking at Sadri over here. In 3D dust mapping, there are people who claim to have samples of their dust maps, where if they could really make these plots of every dimension, they would fail these tests. But the samplings are still useful. This sampling, imagine this sampling took months to make. It's definitely not converged. Does that mean, oh, I have to go for hundreds of years before I can publish my paper? Like, no, I don't think they did. Sadri is like, yes. Spoken like somebody with a faculty job offer. I think one of the things that we haven't worked out as a community, but I'm interested in, is what do you say about this sampling? This sampling still tells you something about your problem. This doesn't tell you nothing about your problem. And I would like to understand what it does tell you about your problem, because we really are in situations in a lot of problems in astronomy where you just will never get a converged sample. Like I believe that the 3D dust maps are in that state. And yet people in the 3D dust map world are making samplings of their dust maps. Those samplings are relevant at showing you the uncertainty. This is showing you that there is an uncertainty on your parameter at this level. It's also showing you that there's kind of 2 modes. So you've learned a lot from this sampling, even though it doesn't actually solve the problem. stated here, it doesn't solve this problem. It does not give you an accurate estimate of your integral, but it does tell you something important about the problem. And I think that's an interesting area for us to be thinking about in research, because we are going to hit this problem. Like, if you happen to have a 9 exoplanet system, like, you're going to hit problems where you just can't sample all of the properties of that thing. You just won't be able to do it. And yet the sampling still might be very valuable for telling you what you confidently and unconfidently know about that system. We're at the time. There's so much going on in MCMC, we could almost do the whole semester on MCMC. Because we haven't even done any of the methods. You're like, what are the methods? What are the references to the methods? Like, how does nested work? Like, that would be a fun, maybe we should get some people who are doing high-end MCMCs to give some presentations in this forum.
Maybe not nested, maybe all the other.
Since you know nested. So this is now Vera decides what she means. No, actually, that is
I don't
true.
know, I mean, you said you don't like the premise, right? And you're not confident that I hear you. What I'm saying is, like, a lot of cosmology community is so used to using it, but we never think about any of these other things. And I think it's really useful to break that.
For sure. Actually, one of the things that I mentioned last week is, and that I'm obsessed with, is I mentioned this work on diffusion that Laurence Levasseur-Perot has been working on. Like, and one of the interesting things is there's a whole set of methods in data analysis that look very much like physics problems. And the idea in MCMC is that the probability, P of theta, is like e to the some energy. The log of the probability is a lot like an energy. And then a correct sampling is one that's in the Maxwell-Boltzmann distribution in that energy landscape. So the MCMC methods are like finding the set of putting molecules into the energy landscape in thermal equilibrium. And then that's a sampling of P of theta. So, and that's why there's all these beautiful connections to physics. And it's really a prejudice that I'm a physicist. And so I like methods that have a description in terms of physics. And Laurence Levasseur, who I was mentioning, has a beautiful talk on how these diffusion methods, which are used in machine learning, are also exact physics models that solve exact data analysis problems. So MCMC and diffusion, which I think is called Langevin sampling when it's used in this context. But anyway, there's several methods now, and then Hamiltonian Monte Carlo. All three of these things are like treating the sampling problem as like a dynamical problem in statistical mechanics. And this convergence is the approach to equilibrium. This is like the gas is settling into equilibrium. So this is like sound waves bouncing around as the thing settles into equilibrium in that context.